Now, I wanted to say hi to everybody who gets together on Facebook, on the podcast group, and talks to each other. If you want to meet like-minded people that listen to Space Nuts, do a search for the Space Nuts podcast group and join fellow listeners, because they're a great community. They have a lot of fun, and they often have a lot of interesting discussions about this, that and the other. I occasionally will pop in and say hello and maybe answer a question. Sometimes questions are directed towards us, and I make Fred's answers up because I just think that's a lot of fun. But yes, it's the Space Nuts podcast group, and you can find it on Facebook. Just put a search in for that. And while we're at it, also hello to our YouTube viewers, who for some reason or another are increasing in number, even though they can see our faces. That is really lovely. So if you prefer the vodcast over the podcast, you can find us on YouTube as well. Now, Fred, something a little bit different this week. We're going to read some questions. We've finally transposed our massive text questions that came on a spreadsheet that basically was 3 kilometres long in one big string, and managed to whittle it down into manageable, edible parts. So let's get into our first question. Actually, it's a double bunger. Both our questions are double bungers this week. First one is from Andre in the Netherlands. Hello, Andre. He says, hello, Space Nuts. I have a few questions for your show which have been bothering me for a while. I'm sorry to hear that. First, our Milky Way has a diameter of about 150,000 light years. I would like to know how thick it is. Well, it is pretty dumb, I will say that. So how high is the cake is his question. Second, I would like to know if the plane of our own solar system is aligned with or tilted in comparison with the centre of our galaxy. And how is this for other solar systems in our galaxy? Are they all the same or different? Thank you, and keep up the good work. A fan of your show. Andre, thank you so much. Well, we might as well start with how thick the Milky Way is.
I think I'm
guessing he means top to bottom.
Well, in your thinking, he means in terms of its intellectual capacity, I guess, but that it's pretty dumb.
No, I'm thinking he's
about
the height.
Have you got any guesses, Andrew?
Well, if it's spread out 150,000 light years, I'm going to guess probably a quarter of that.
Yeah, that's an interesting guess. So we should make it clear that we're talking about the disk itself rather than the halo, because there is this halo which is nowhere near as dense as the disk. It's much more, the stars are much more sparsely spread out. It's where the globular clusters are that I mentioned a few minutes ago. And that's more or less spherical. So, it's probably 150,000 light years top to bottom. But when you come to the disk, the answer is a lot more interesting and just a little bit more complicated, because we define, and this actually comes from work that I wasn't directly involved, but friends of mine, people I work closely with, certainly were. It's got various components, and it depends which ones you're talking about. So yes, 150,000, maybe even 200,000 light years in diameter. It's growing all the time, or at least our estimate of it is. The thinnest component of the disk is called the young thin disk. So there's two bits. There's the thin disk and the thick disk. But the young thin disk is where star formation itself is taking place now, and the Milky Way's youngest stars are, as well as most of the gas and dust. It's the bit that we see when we look along the centre of the Milky Way, and that the thickness of that is only about up to about 500 light years, maybe less, maybe more like 300 light years. It's really very, very thin, almost like a blade through space when you think about it, given how big the diameter is. And then there is an older component which is called the old thin disk, and that's stars that have basically migrated away from the young thin disk, so they're older stars, and that's roughly 1,000 light years thick.
Okay.
And then there is what we call the thick disk, which and it was the difference between the thin disk and the thick disk discovered by scientists who I used to work with in Edinburgh, actually, years ago. About, gosh, it's more than 30 years ago. It's a long time ago. But that the idea of the thin and thick disk is, as I said, it's been around for quite a long time. Neil Reed and Jerry Gilmore, I think, were the proponents of that, people I worked with in Edinburgh. Still going strong in the world of astronomy. The thick disk is thicker, and it is round about something in the region of 5 to 10,000 light years. So, it's probably about 5,000 light years thick. Compared with 1,000 for the old thin disk and something like 300 for the young thin disk. So the thick disk is very definitely a separate component. The work that I did with colleagues in the RAVE project, the radial velocity experiment that we did using the United Kingdom Schmidt telescope, we collected the speeds and physical parameters of 500,000 stars, and it was possible from the results of that to see the delineation between the thin disk and the thick disk, even though we actually tried to avoid the disk because there are too many stars in it. We were mostly looking at the halo of the galaxy with that experiment.
Yeah.
Anyway, a great question, and thank you for that. Moving on to
sorry, I just need to clarify.
Yeah.
When we're talking thick disk and thin disk, are we talking layers?
Yes, in a sense we are. I mean, it's all done because you're talking about stars, which are individual objects, and not, something like gas. You're really talking about statistical things. But so the statistics are that there are a lot more stars in the thin disk than the thick disk, and you can imagine it as a layer between one and the other. It's probably not a very flat layer because, once again, there's probabilities involved. But really remarkable that we can now recognise these two characteristics of the disk. In fact, we recognise too that the halo itself is not uniform. There's certainly an inner halo and an outer halo, and they've got quite different rotational characteristics. So as we find out more about our galaxy, we realise its structure is more and more complicated.
Yeah, well, why am I surprised? Yeah.
Yeah.
Now, he also wants to know about how the solar system is aligned or tilted in comparison with the galaxy, and is it the same for other solar systems?
The answer to that is no. The answer to the tilt of our own solar system is that the plane of the planets, what we call the ecliptic plane, is tilted to the plane of the galaxy. In other words, to the thin disk. It's tilted at an angle of 60 degrees, so it's sitting up at an unusual angle, nowhere near the same plane. And that is true of all solar systems. We find that they are at various different angles. I think people have looked for the kind of correlations that might say, 60 degrees is the most popular and there must be a reason for that. That's not been found. So yes, you have quite a strong tilt of the solar system to the plane of the galaxy,
and that is normal.
Yes, and that's normal, and it seems to be what you've got. You remember how the solar system was formed. You start off with a cloud of gas and dust that collapses under its own gravity, and it's the little random rotations within that cloud that eventually take on a preferred direction and a preferred plane of rotation, so the whole thing starts rotating. That could be in any direction, and that's why we get this randomness. It's a great question.
Okay.
Very, very nice to have Andre's question about it.
Indeed. Thank you for the question, Andre, and hope we adequately covered your two elements today. Let's move on to a question now, a couple of questions from David in Springfield. He describes it as a dark matter quandary. Evidence for dark matter was found by observing that the stars of galaxies all move at the same speed regardless of whether they are near or far from the galactic centre. How then does a spiral galaxy even form with all stars moving at the same rate? Like water spiralling down a drain, the spiral shape requires the stuff towards the outer edge to be moving more slowly than the stuff near the centre, right? Dark matter should make formation of spiral galaxies impossible. Why aren't all galaxies of the non-spiral globular type if dark matter is real? And another question from David on the subject of terraforming Mars, which we touched on earlier. The red planet has a very thin atmosphere. Terraforming would have to invoke creating a practical atmosphere at a density more like it used to have a long time ago. With Mars having such low gravity, wouldn't any increase in its atmosphere we engineer just evaporate back into space like its original one did? If so, would the rate of that evaporation be at such a slow rate that we could maintain it, kind of like having a slow leak in a tyre, you just keep adding air once in a while? Yeah, I like that question.
I do. We'll
get back to that. But yes, I've got a feeling the answer to the first question is that spiral galaxies are a trick of the eye, which I think we talked about a few weeks ago. The spirals can only be seen under certain circumstances, and all galaxies aren't actually spiral galaxies. Is that what we said?
That's more or less it, yes, in the sense that the spirals are in some way an optical illusion. What David says is absolutely right, although I think the premise of what he's saying is wrong, because yes, he's correct in that the rotational speed of stars nearer the centre is more or less the same at the outer edge, but if the spiral was a physical property of stars, then you would still get the winding up effect, because the inner stars have got they have a much shorter distance to go around once than the outer stars, even though they're all rotating at the same speed. It's not rotating like a solid body. It's rotating with the linear velocity of all the stars being effectively the same speed, roughly 250 kilometers per second. And even in that circumstance, you would get a wind up of the spiral arms, and in fact it would be wound up so tightly that's how we know that spiral arms are not just strings of stars, and as you alluded to, it's something else. And what we're seeing with the spiral is this wave of higher density moving through the disk of stars and gas, and as it moves through the gas, the pressure triggers star formation. You get all these high mass short-lived stars which burn over only a few tens of millions of years, then blow up as supernovae, and you get this brilliance forming along the spiral arm. So the spiral arm is a wave, we call it a density wave, and that's why you've got these beautiful gentle spirals rather than something really tightly wound in a galaxy, which is what you'd get if they really were strings of stars, because they're moving at the same linear speed, but the inner stars have got far less distance to go than the outer ones, so they immediately pull it into something looking like a clock spring, whatever a clock spring is. People don't know what clock springs are these days. I remember them well. Anyway, that's
young whippersnappers don't know what a clock spring is.
Right, yes, indeed. It's not the case that dark matter would make the formation of spiral galaxies impossible. In fact, it probably enhances it by it may well be that the dark matter halo of galaxies stabilizes the density wave and gives it that stunning property that we see in galaxies like M81, which is one of my favorites. It's got a beautiful spiral structure. Hope that answers the question.
Hopefully.
Moving along to terraforming Mars.
Mars. Now, you said earlier impossible, but he brings up a couple of interesting concepts which we should discuss. But let's say we did terraform Mars and we did create an atmosphere. It couldn't hold.
That's right. So what he's saying is exactly right. The density, the gravitational pull of Mars is insufficient to hang on to an Earth-like atmosphere. You lose the oxygen and the nitrogen very quickly. The evidence for that is sort of ongoing as well, because the last remnants of Mars's thick atmosphere are still disappearing into space. The Marvin spacecraft can detect oxygen, I think hydrogen, oxygen leaving the planet, being basically released from the planet now. So terraforming is a challenge. If you want to turn its atmosphere into an Earth-like atmosphere, you've got to do what David suggests at the end of his question there. Could we still maintain it because of the slow rate of evaporation? Well, I think the answer is maybe, but where are you going to get all this carbon dioxide from that you need to stabilise the atmosphere? And my guess, his lovely analogue of a slow leak in a tyre, which I like very much. You just got to keep pumping it up. I think you'd probably have to pump it up faster than I think you'd struggle to pump it up faster than the leak. That's the bottom line.
Yeah, I think you're right. Yeah. My theory is if we ever did go to Mars to put a permanent human presence there, you'd probably live in domed communities or something. You'd create an artificial environment and live in domes over the surface, and I think that'd be the only way to make it feasible, and even that would be a major engineering challenge. But who knows? One day that might just be the case. Yeah.
Well, my view on all this, that the ethical way to colonise space is to build megastructures, like Halo worlds, which has engineering that's probably not that much different from trying to terraform a planet. In fact, terraforming a planet will be much more of a challenge. Interesting stuff. But I think you're right. I think domes on Mars are what we're going to see eventually when we get research stations there, perhaps. I hope we never try and colonise the planet, but if we get research stations, which I think is a good idea, we'll have humans living there, and they'd have to be radiation protected as well. That's the other problem with terraforming it. How do you generate a magnetic field? Because you need that to protect the atmosphere as well as everything else.
We get lots of space wheelbarrows, and we just demolish Mercury or something and add it to Mars.
I've heard that sort of thing before. Oh dear, we tow Mercury out to Mars. What?
Or just ram them together and just wait a couple of billion years for it to settle down.
Yeah. Anyway,
that'll work. Anyway, there you are, David. Hopefully we helped you out with your inquiry, and thanks for sending in your questions. And that brings us to the end, but don't forget, if you do have some questions for us, you can do that on our website. Just go to spacenutspodcast.com, and you can click on the little tab that says AMA, which I'm doing right now as we speak, and it brings up the interface where you can either type a question in the old-fashioned way using our email interface. Whoever would have thought the day would come where I refer to typing an email as old-fashioned? But the other option is, if you've got a device with a microphone, you just press the start recording button and it will record what you're saying. Don't forget to tell us who you are and where you're from and ask your question, and boom, all done. Simple as that. And while you're there, don't forget to visit the Space Nuts shop. There's all sorts of goodies there that you might like to add to your repertoire of useless junk at your place. But you'll be helping us out at the same time. But check it all out at spacenutspodcast.com. And Fred, that brings us to the conclusion of another episode, 247 of the Space Nuts podcast. Thank you, sir, and it's been great fun as always.
And thanks to all our listeners for sending in their questions, and we will get to more next week.
We will indeed.
See you later.
Thank you, Fred. See you next time. Bye-bye. Fred Watson, astronomer at large, part of the trio that creates this podcast. And hello back in the studio to Hugh. It's not actually a studio, it's a back shed, and he shares it with the dog. But that's okay, plenty of dust there to put on Mars. But from me, thank you again for watching or listening and contributing, and we'll see you again next time. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.